Hello everyone. So it is a pleasure to be with you today at E-PiCo Winter School 2022. I am Houssein AL-ATTAR, PhD student at École Centrale de Nantes in the frame of the share between Renault and Centrale Nantes, supervised by Malik Ghanes as thesis director and Mohammed Hamida as co-supervisor, and Miassa Talib and Abdel Malik Maloum from the side of Renault. So I will share my screen. Is it okay for the sharing?
Yes, perfect.
Very good. So I will present to you in this presentation my PhD topic about electric vehicle bidirectional charger control. I will divide my planning into many sections. Firstly, a general overview in the introduction. Then the problem statement will be announced. Then in the other sections, I will present to you the different modulation strategies applied to the DC-DC converter, an optimized converter design, and some robust control strategies. And also we will see the bidirectional EV charger control in the whole charger, electric vehicle charger, and some other different topology, some different topologies of the EV charger. So let's start firstly by the general introduction, just to present the system. Firstly, as you know, the energy transport is today a key subject of the energy transition. Electric mobility represents a significant technology of transport for the society, resulting in more efficient mobility. This technology, in fact, is mainly supported by the electric vehicle, EV. And it should be noted that this PhD work, for sure, was supported by the project share between Renault Group and École Centrale de Nantes about the electric vehicle performances improvement. So in fact, for the EV charger in general, the well-known mode is G2v mode, or grid to vehicle. This means this mode which represents the battery charging mode. The batteries are charged from the smart grid through chargers to charge the battery in the EV. However, it is possible to send energy in opposite way, which arises the concept of discharging mode, that is from EV batteries to power grid, that is V2G, or vehicle to grid. This technology is growing in importance today because it offers many advantages related to the improvement in performances of the electricity grid, the efficiency, the stability, and the reliability, but also for the tracking of variable renewable energy sources. So in fact, for the EV operating modes, there are many operating modes. The well-known is G2v mode, or battery charging mode, but there are, in the discharging mode, many different operating modes like V2G, or vehicle to grid, but also vehicle to home, or to load, or to another vehicle maybe. So in one word, we can say that is vehicle to everything, or V2X mode. So for the charger topology, before to present to you the charger topology in general, it is very important to give you the general overview about the structure of the charger. So the charger topology is mainly based on the power electronics. This means the technique of modification of the presentation of electrical energy via switching. So the basic component of the power electronics is for sure the power converter, which is operating as a switch, close it or on, or open it or off. So the power converters in the EV charger are divided into two parts. The first one is the AC-DC converter, and the second one is the DC-DC converter. So like this figure, you have here the EV bidirectional charger structure in general. You have here the AC grid. Then you have the bidirectional AC-DC converter. you have the DC bus link between the AC-DC and the DC-DC converter, and you have at the end the battery. For each converter, we should implement a specific control strategy using the controller. This means to derive or to send our control signals to derive the MOSFETs to do the switching based on the experimental validation and experimental setup. So for the EV charger in general, there are two types. The first one is which called the DC chargers or the off-board chargers. This means when the charger is outside of the vehicle. The main advantage of this type is to remove weight, to guarantee higher power transfer, but the drawbacks, it is expensive for sure, and it is not universally available. On the other hand, you have the AC chargers. The main advantages, firstly, the main drawbacks are the weight adding to the vehicle, because it is inside the vehicle. You have lower power transfer than that in the DC charger case. But the main advantages are the charging at any place where electric outlet is available. So here in our PhD, we will focus on the onboard charger and especially on this AC3 EV charger, which is divided into two parts. The first one is the AC-DC converter related to the Vienna topology. This means you have here the PFC, power factor correction as AC-DC converter with the Vienna topology. And you have the Dcdcllc converter. Our topology used in the Dcdcllc converter is which called the Llc Resonant Converter. By focusing on this Dcdcllc converter topology, means the Llc Resonant Converter, we have this topology here in this figure. You have in the resonant tank, in fact, you have two full bridge separated by a resonant circuit and a high frequency transformer to guarantee the galvanic isolation. So here you have the DC bus voltage, and here you have the battery voltage, and here the Dcdcllc converter structure. So in the circuit, in the resonant circuit, you have a capacitor in series with the inductor and a parallel inductor in parallel with the transformer. And here you have the capacitor of the DC bus link, and here you have the battery voltage. So in the state of the art, first, it is important to show you the different strategies used or mentioned in the state of the art before to highlight our contributions in this PhD. So in the literature, there are many research studies about the control of the Dcdcllc converter or the EV charger in general. For example, the classical control laws like PI controller to regulate the resonant current. The resonant current, this means the current flows inside the resonant circuit by varying, for example, the phase shift, or for example, a battery voltage regulation also with a PI controller by varying the DC bus voltage. But the main limitations of the literature are a battery voltage regulation, if it is not imposed, or a DC current regulation, when or where the battery voltage varies over a narrow range or a reduced range between 12 and 120 volt. But in fact, in our studied case, this means the EV charger application, we need to regulate the DC bus voltage, where our output voltage is imposed by the battery management system, BMS, and we have a wide battery voltage variation. In fact, it is a wide operating zone variation for the EV charger, where the battery voltage varies between 240 and 440 volt, and the power varies between 0 and 11 kilowatt for the one-phase charger, and between 0 and 22 kilowatt for the three-phase charger. So for the PhD goals, in fact, the first goal is to avoid the existing drawbacks of the bidirectional charger, to improve the efficiency and the control performances, to model the AC/DC and the DC-DC converter in order to implement and to design some control laws in the two different modes. This means G2v and V2X mode, and to present also some advanced and robust control strategies, and for sure to validate this control strategies at the end. So the main contributions are firstly wide variation in both battery voltage and battery power or charger power with respect to the literature, and especially in V2X mode. We have to improve the DC bus voltage control for the entire operating zone. There are many control strategies implemented based on which called our Dcdcllc transfer function gain inversion method. We also worked about the optimized design of the hardware system of the Dcdcllc Resonant Converter. And the new challenge here is to include the control constraints in the optimization problem. And also, on the other hand, some robust control strategies are designed and implemented to improve the control performances against the disturbances, any unexpected modification, or, for example, parameter variation. The aim, in fact, is to improve the control performances and the efficiency of the bidirectional EV charger. So here, let's announce the problem. So firstly, in order to implement any control strategy, it is very essential to define a dynamic model. So here for the Dcdcllc converter, there are two modeling approaches. Firstly, the large signal model. In this modeling approach, we have some nonlinear dynamic equations. We can obtain a nonlinear complex model, but for sure, the main drawback of this modeling approach that the control design will be more complex. On the other hand, the small signal modeling, we have here some harmonic approximation, and especially first harmonic approximation, FHA. So here, the idea is to obtain a system with transfer function representation to be more favorable with the control design. But for sure, the main drawback is the operating zone limitation. So as you see here, there is always a compromise to do between the control and the model, and for sure, the requirements. So for the Dcdcllc converter, let's focus firstly on the small signal modeling. So here, based on the first harmonic approximation, the input voltage modeled here, the input voltage of the resonant circuit means V1 is modeled as an ideal sinusoidal voltage source, because in fact, it is a square voltage source resulted from the switching operation of the MOSFETs in the primary bridge. But with the first harmonic approximation, we can assume that this input voltage V1 is modeled as an ideal sinusoidal voltage source. The second assumption that the output filter capacitor and the MOSFET's effect are ignored in the small signal modeling. So with these assumptions, in fact, we can obtain our equivalent circuit for the Dcdcllc converter. So here we have the input voltage, we have the resonant circuit, the capacitor, and the two inductors in parallel with our resistor, which depends on the battery voltage and the converter power. This in the G2v mode. So this means the input voltage is from the DC bus voltage side, and the output is from the battery voltage side. So in G2v small signal modeling, we can obtain this LLC voltage gain transfer function based on this equivalent circuit, which depends on the LLC parameters and for sure on the switching frequency, because S, it is equal G omega, which equal to 2 pi F. F is the switching frequency. And also like G2v mode, here we have in the V2X mode, we can, based on the small signal modeling, we can obtain a representative or an equivalent circuit of the LLC converter, where here the input voltage of the resonant circuit is from the battery voltage side, the output voltage is from the DC bus voltage side, and here the resistor depends on the DC bus voltage and the converter power. And also we can obtain our transfer function in V2X mode, which depends on LR, CR, and the resistor, because here the input voltage will be in parallel directly to the inductoral M. So the most popular modulation strategy included or used with the LLC converter is which called pulse frequency modulation, or PFM. In fact, this modulation strategy consists of varying the switching frequency of MOSFET control signals with fixed pulse widths or fixed duty cycle at 50% or at 0.5. So with this modulation strategy, in fact, by using the equivalent circuit of the LLC converter using the small signal modeling in V2X mode, we can obtain our switching frequency using which called the gain inversion method. This means based on this transfer function gain, where S is equal omega G, omega is a 2 pi F, F is the switching frequency. We can, by gain inversion, we can obtain our which called feed-forward frequency F0. So this means the switching frequency obtained by the gain inversion. So here in this strategy, in pulse frequency modulation, it should be noted that our feasible operating frequency zone is between 60 and 200 kilohertz. This condition is to respect or to guarantee the zero voltage switching or ZVS operation or property to improve the efficiency of the converter. This means to reduce the switching losses. And based on this PFM strategy in V2X mode, we can, by calculating our feed-forward switching frequency, we can see here in this figure the feed-forward switching frequency with respect to the variation of the battery voltage and the converter power. We can see here that there is a high frequency saturation zone, the yellow zone in this figure, where in this, and the other zone is the feasible zone, when we can apply the PFM strategy. In the yellow zone, this means in the high frequency saturation zone, there is a low efficiency and there is a DC bus voltage regulation loss with the PFM strategy. So to avoid this problem, we have to present some other modulation strategies. So firstly, just for the PFM control strategy, in fact, we have here the gain transfer function. Based on this gain inversion, we can obtain our feed-forward switching frequency. And by adding this switching frequency to the output of the PI controller, we can obtain our controlled switching frequency. To highlight the problem statement, we can see here by, for example, with an operating point in the feasible zone, not in the yellow zone, in the feasible zone with the battery voltage 350 and power 9 kilowatt, we can obtain, for example, a controlled switching frequency in our feasible zone here between the green line and the yellow line. The red one is feed-forward switching frequency, and the blue one is a controlled switching frequency with a closed loop control. Here in this operating point inside the feasible zone, we can control the DC bus voltage and we can obtain good control performances. However, with an operating point in the saturation zone, this means with a battery voltage equal to 350 volt and power equal to 2 kilowatt. This means an operating point in the yellow zone, in the last figure, or in the saturation zone. We can see here that our feed-forward switching frequency F0, it is 275 kilohertz. This means out of our feasible zone. So here the controlled switching frequency will be saturated at 200 kilohertz to respect the feasible condition. This saturation causes an important regulation error in the DC bus voltage control. So in summary of this PFM control strategy, we can say that the control frequency range is not sufficient to reach all the operating points. So for this reason, we need to present some other modulation strategies to avoid the PFM strategy limitations. And for sure, there are here two modulation strategies proposed, which are called fixed switching frequency strategies. Let's start firstly by the pulse width modulation, or PWM. This means this strategy consists of varying the duty cycle and with fixed switching frequency. So now the switching frequency is constant and the variable is the duty cycle D. So the DC bus voltage can be regulated by varying the duty cycle. We can obtain also, based on the small signal modeling, we can obtain a new gain formula with the pulse width modulation, which depends on the duty cycle D, and G is the gain defined in the PFM case. Based on also a gain inversion method, we can obtain our feed-forward duty cycle D0 by the gain inversion of the G prime. And by adding this D0, this feed-forward duty cycle, to the output of the PI controller, we can obtain our controlled duty cycle. The main constraint of this strategy is a wide variation of the duty cycle, because in fact, this strategy is based on the first harmonic approximation. This means to respect the small signal modeling, we need to obtain a proper resonant operation of the LLC converter. We need to obtain a proper sinusoidal voltage waveform. So to guarantee the ZVS, or the zero voltage switching, the duty cycle must change around 0.5, and this condition represents the main drawback of the PWM strategy. To avoid the PWM strategy limitations and to solve the PFM drawbacks, the PSM strategy, or the phase shift modulation strategy, is one of the efficient methods to obtain a fixed switching frequency operating. So here with the PSM, we have a fixed duty cycle at 0.5. We have a fixed switching frequency, and now the variable is the phase shift angle between two MOSFET control signals, the theta, the controlled phase shift angle between left and right arms in the identical H bridge of the LLC converter. Also, based on the small signal modeling, we can obtain now a new gain formula for the PSM strategy, which depends on the controlled phase shift theta, and this phase shift varies between 0 and 0.5, and we can obtain our closed loop control block by the gain inversion method. We can obtain theta 0. By adding theta 0 to the output of the PI controller, we can obtain our controlled phase shift angle to regulate the DC bus voltage and to cancel the static voltage error. So after definition of the parameter settings in MATLAB Simulink, a comparative study is generated between these different strategies, PFM, PWM, and PSM. We can divide our comparison criteria to two parts. The first one is the control performances, like the overshoot percent, the rising time, the convergence times, or the steady state DC bus voltage tracking error. And on the other hand, a comparative study is generated with respect to the LLC converter efficiency. So firstly, about the control performances, in this figure, we have the DC bus voltage responses with each modulation strategy, in red with the PFM, in green with the PSM, and in Magneta with the PWM, with an operating point inside the saturation zone. This means 300, for example, 350 volt, 2 kilowatt. We can see that the PWM and the PSM strategy can avoid the DC bus voltage regulation loss with the PFM strategy. In this table, we can see the different parameters of the comparison with respect to the DC bus voltage tracking error, the convergence time, the overshoot percent, the rising time, and the efficiency. We can see, for example, that the PSM strategy is faster than the PWM strategy with respect to the rising and the convergence time, but the PWM strategy is better with respect to the overshoot percent. In PWM and in PSM strategy, the switching frequency is fixed at 200 kilohertz. In PFM strategy, we have a saturated switching frequency, which causes the DC bus voltage regulation loss. Here, a comparison between the different strategies in terms of the efficiency. We can see the efficiency in function of the power, which varies between 2 kilowatt and 11 kilowatt. We can see that at low powers, in green here we have the PSM, in red the PWM, and in blue the PFM. At low powers, we can see that the high efficiency degradation with the PFM strategy, no efficiency improvement with the PWM strategy because the duty cycle constraint, the wide variation out of the ZVS zone. Whereas with the PSM strategy, there is an important efficiency improvement. For example, for 2 kilowatt, we have 90 to 92% as an efficiency with the PSM strategy. On the other hand, at high powers, we can see that there are high efficiencies with the different strategies because we are in the case of the feasible zone. So no, not in the case of the saturation zone. So here in the last part, I gave you just an overview about the different modulation strategies applied to the LLC converter. This means in the point of view of the control or software. But we worked also in the point of view of the hardware solutions. This means how we can obtain the minimum parameters of the LLC converter, how I can change my LLC parameters to obtain good control performances and to reduce the conduction on the switching losses and to obtain a better efficiency. So now in this section, I will present to you an optimized converter design method based on the small signal modeling of the LLC converter in G2v and V2X mode. In each mode, we can obtain our transfer function gain, which depends on the LLC parameters, on the Llc Resonant Circuit parameters. So this means based on the gain formula in G2v mode, we can define the equation that gives the switching frequency or the feed-forward switching frequency. The parameters of this equation depend on the LLC parameters. This means LR, CR, and LM. And also in V2X mode, we can define our control stability equation that gives our switching frequency in V2X mode. Now, based on the gain inversion method, we can see here that in G2v mode, the feed-forward switching frequency in function of the power and the battery voltage present a small saturation zone in G2v mode, whereas in V2X mode, it presents this high saturation zone, the yellow zone, because the feed-forward switching frequency here depends on the parameters of the resonant circuit, on the demanded power, on the DC bus voltage, and the battery voltage, because here the feed-forward frequencies are the solutions of the control equations. So they depend on the LLC parameters. From here, the optimization idea becomes, because now the LLC converter parameters, this means CR, LR, and LN, are an important effect on the onboard charger performances. They are an effect on the control feasibility for the wide operating zone, and also they are an effect on the onboard charger sizing. This means the cost. So the main contributions of this optimization problem is firstly to design an optimization methodology to minimize the Dcdcllc converter cost. This means to obtain the optimum values of the LR, CR, and LM, but at the same time to improve the efficiency. This means the new challenge is not only to design the resonant circuit of the Llc converter, but also to guarantee the system stability over the wide operating zone in the two modes simultaneously. This means in G2v and V2X mode. This means the aim is to obtain the optimum LR, CR, and LM, the LLC parameters, to minimize the charger cost and to improve the control frequency feasibility in the two operating modes. So let's define our decision variables for this optimization problem. X, the LLC parameters. The omega-1 is the feed-forward frequency in G2v mode. Omega-2 is the feed-forward frequency in V2X mode. In function where the battery voltage and power varies in a specific range, we have now our decision variable with the two index I and G. I with respect to the battery voltage and G with respect to the power. We can define now our objective function F in function of the X1, X2, X3, and the new challenge is to add the two control equations C1 of X and C2 of X. C1 is the equation which defines the feed-forward switching frequency in G2v mode. C2 of X is the equation which defines the feed-forward switching frequency in V2X mode. So now, by defining the hardware requirements, the control constraints, we can obtain our global minimums. This means the optimum values of the LLC parameters, which minimize the sizing of the LLC converter and also improves the control frequency zones. This means improve the LLC efficiency. After definition of the parameter settings table, by solving the optimization problem with MATLAB optimization solver using fmin_con, we can see here that the new feed-forward switching frequency in function of the battery voltage and the converter power with the global optimized mean values in the figure E, and the last figure of the feed-forward switching frequency with the actual values in figure F. We can see that there is an improvement of the control frequency feasibility zone. We have just a small saturation zone at 60 kilohertz instead of the 200 kilohertz, and the saturation zone is reduced with the optimized mean values resulted from the optimization algorithm. And also in G2v mode, we can see that now our feed-forward switching frequency is in the feasible zone for the whole operating zone, instead of by comparing it to the G2v feed-forward frequency feasible zone with the actual values where there is a small saturation zone. So here also there is an efficiency comparison between the LLC parameters or the LLC behavior with the optimized values in red one, and the LLC behavior with the initial values in blue one. We can see that with the battery voltage equal to 350 volt, for example, we have here in figure I an efficiency comparison with respect to the power variation in G2v mode, and in the figure G, an efficiency comparison in V2X mode. We can see that the red one, this means the efficiency with the optimized values, presents higher values than that with the initial values. So now let's give you a general overview about the robust control strategies. Why the robust control strategies? Because with the LLC converter system, it is in fact related to the EV charger. In the EV charger application, we can, for example, we can have an expected modification, or for example, an error, a measurement error from the sensor, or an uncertainty in the parameter, in the parameter value, some uncertainties. So for this reason, we need to design robust control strategies. For the LLC converter, for the DC-DC converter, the modulation strategy here obtained or adopted the phase shift modulation, or the PSM strategy, because it gives the highest efficiency in the whole operating zone. The existing control is a PSM based on the small signal model using the classic control laws like PI control. Now the goal is is to provide some robust control strategy to guarantee the DC bus voltage tracking, but also to provide the control robustness against the unexpected disturbances and the LLC parameters variation or uncertainty. So one of the robust control strategy, one of the proposed robust control strategy is the model free control NFC, and also the adaptive super twisting sliding mode ASTSM. So let's focus on the NFC. Here we have the LLC equivalent structure in V2X mode. We have here the square voltage at the input from the battery side, which varies between VBAT and minus VBAT. We have here the transformer, the resonant circuit of the LLC, and here we have the capacitor voltage, the DC bus capacitor, and the resistor, which replaces the AC-DC converter, and the DC bus voltage. We can here define our LLC dynamic equations in figure A, and based on these dynamic equations, we can say that any dynamic equation, any model can be represented by some differential equations, or maybe one differential equations, which it is a link between the output and the control, the output Y and the control U. This is the main idea of the NFC, because we can replace our dynamic equations by only this ultra local model, a one equation which links the output and the controlled variable U, and F is a parameter which, like a black box, which contains all the informations of the model. So now the idea is to estimate the parameter F to avoid the mathematical model identification. And here in the equation D, here it is the NFC control, or the model free control U, the control variable with respect to the ultra local model. We can define directly our model free control. For the LLC converter case, for our application, we can see here that this NFC strategy block is divided into two parts. The first one is to design the feedback control to guarantee the DC bus voltage tracking, but the other part is to estimate the parameter F to provide the control robustness against the disturbances without any prior knowledge of the LLC model. A comparative study here is generated by adding a current disturbance at 0.0 current second. We can see in red the NFC, the DC bus voltage response with the NFC, in the green that with a PI, with a simple PI controller, and in Magneta that with a gain inversion, the gain inversion method. We can see that the DC bus voltage response with the NFC presents the efficient response with respect to the other strategies, and it is robust. It is the robust one compared to the other strategies. And also here, by adding at 0.03 second, by adding a sinusoidal perturbation to the DC bus voltage request, we can see that the DC bus voltage response with the proposed NFC can follow, remains controlled, in fact, with the NFC, whereas with the other strategies like PI or GI, we have an important DC bus voltage tracking error. So we can say here that the model-free control is robust with respect to these disturbances. So also, let's give you just a quick idea about the bidirectional EV charger control. Here we have our EV charger structure, the AC3. We have the AC-DC converter, and we have the DC-DC part. So the main idea here is to control the EV charger in the two modes, in the G2v and the V2X mode. Firstly, for the PFC, or for the AC-DC converter, we have this control system. Just to do a zoom. So here, based on the after generation of our current reference, we can implement a current regulator. This means the idea of the AC-DC converter is to regulate the grid current, and the idea of the DC-DC converter is to regulate the DC bus voltage. So here with the PFC topology, we can implement a current regulator to generate our duty cycle D, to generate our pulse width modulation and to generate the MOSFET control signals of the PFC. On the other hand, for the DC-DC LLC converter, the main idea is to regulate the DC bus voltage by varying the switching frequency. So here, the existing control consists of using the PWM control to regulate the grid current by varying the duty cycle of the PFC, and by using PFM strategy to regulate the DC bus voltage by varying the switching frequency of the LLC converter. In the G2v mode, the proposed control strategy consists of regulate the DC bus voltage and the current grid with the PFC in case of saturated LLC switching frequency, because in the case of an operating point in the saturation zone, we have a regulation loss, a DC bus voltage regulation loss with the PFM strategy. So here the new challenge is to add the DC bus voltage regulator in the current regulator as a backstepping control to generate the necessary duty cycles to regulate the DC bus voltage and the grid current using the PFC stage or the AC-DC converter to improve the DC bus control and to avoid the saturation problem with the DC-DC converter. In the VDG mode, the new challenge is to use PWM with the PFC, but the PSM with the DC-DC LLC converter. This means the phase shift modulation to avoid the problem of the PFM and to obtain a good control performances of the DC bus control and the current grid control in case of saturated LLC switching frequency. So here also we focus on another charger topology. This means which called the charger topology with DAB converter or dual active bridge converter. In this figure, this is a topology of DAB. It is DC-DC converter with only an inductor in the main circuit of the DAB, with the two full bridge separated by a transformer. So also we focus on different charger topology using the DAB converter. The work planning is divided into many parts to implement different modulation strategies like single phase shift or dual phase shift modulation, and also to generate a comparative study between the different modulation strategies to do at the end a hybrid, a hybrid control strategies to choose the best modulation strategy according to an optimization strategy based on the requirements. At the end, for sure, the aim is to validate our strategies using the experimental setup. So using the EV charger setup with our laboratory in the frame of the chair of Renault, Centrale Nantes. So here the aim is to validate the results, but with the experimental setup at the last phase. So in summary, as conclusion, we can here highlight the main contributions of our PhD. We can say that a control loss design in V2X mode based on the transfer function gain. This means based on the small signal modeling with wide variation of battery voltage and power is done. The different strategies, the different modulation strategies like PFM, PWM, and PSM are implemented and compared with respect to some criteria like control performances and the LLC converter efficiency based on the small signal model. On the other hand, an optimized design of the bidirectional LLC converter for the EV charger application is highlighted. The optimization strategy, the new challenge with the optimization strategy is to include our control equations, our control feasibility equations in the objective function to minimize the cost of the EV charger and to guarantee the control performances, to guarantee good control performances. And also at the end, some robust control strategies like model-free control or adaptive super twisting sliding mode control are designed and implemented to guarantee the tracking, the control tracking, and also the robustness against the different disturbances, the different unexpected modification in the EV charger. Also the EV bidirectional charger control. This means a controller for the AC-DC and a controller for the DC-DC, or maybe a one control strategy using the AC-DC to avoid the drawback of the DC-DC converter are designed and implemented. And at the end, thank you for your attention. And if you have any question, I am ready to answer you.
Thanks, Houssein, for your presentation. Do you have any questions?
So don't hesitate if you have any question.
I check on YouTube at the same time. No, I have no question on YouTube. Feel free to ask anything to Houssein. He was a student in Centrale Nantes as well.
So as mentioned earlier, we can see that in this PhD in general, it is an application of the control of the automatic in the electric vehicle domain, the electric vehicle charger domain. So it is very important because it has many main lines, if I can say, many main lines related to the modeling, to the control system, to the optimization. And so it is very, very important to apply the control strategies in this interesting application, electric vehicle charger.
I have a question for you, Houssein, from the YouTube chat. Could you explain bidirectional Dcdc resonant LCC converter briefly?
The bidirectional Dcdcllc converter?
Yeah.
So here, in fact, this is a topology of the bidirectional Llc converter. You have, in fact, two full bridges separated by a resonant circuit and a transformer. In the G2v mode, the primary full bridge, we can regulate the MOSFETs of the primary full bridge, and the secondary full bridge is used for the rectification. This means only the diodes are on in the G2v mode, whereas in V2X mode, the secondary full bridge is used for the regulation, to generate the MOSFET control signals from S5 to S8. And the primary full bridge is used for the rectification. This means only the diodes and the primary side are used for rectification in V2X mode. So the LLC, in fact, the Llc Resonant Converter, the LLC award becomes from the fact that we have here a capacitor in series with an inductor and a parallel inductor in parallel with the transformer.
Great, thank you. I don't have any other question on the chat, and I'm not able to ask you any questions.
I have a question.
I have a question.
Can you please go over the switching modes? You had PFM, PWM, and then PSM.
Yeah, exactly.
The PSM is what exactly?
So firstly, the PFM, the pulse frequency modulation, is a modulation strategy that consists of varying the switching frequency with fixed duty cycle. So here the duty cycle is fixed at 50% or 0.5. The switching frequency is our variable. But with the PWM or the pulse width modulation strategy, the control or the variable here is the duty cycle. The switching frequency is constant, is fixed here. In the phase shift modulation or PSM, the control variable is the phase shift angle between the MOSFET control signal, sorry, this means theta. Here, the switching frequency is fixed, and the duty cycle also is constant and fixed at 0.5. So with the PSM, we have a fixed switching frequency and fixed duty cycle, unlike PFM and PWM.
Okay, is there a possibility where you have PWM and PFM working in hybrid?
Yeah.
And what are the advantages over PSM?
In fact, with the PFM strategy, we have some limitations related to the saturation of the switching frequency. Because here, for example, in this figure, you have the switching frequency in function of the battery voltage and the power. We can see here that in the yellow zone, this is our saturation zone. This means what? This means the switching frequency is saturated at the maximal authorized switching frequency. So this saturation condition causes a voltage regulation, an important voltage regulation error and a low efficiency. For this reason, we need to improve the control performances and to improve the efficiency by using different modulation strategies like PWM and PSM strategies. With the PWM, also there is a drawback. The main drawback is a wide variation of the duty cycle, because you need to respect the first harmonic approximation. To respect the first harmonic approximation, this means to minimize the switching losses, the duty cycle must change around 0.5. Okay, when we have a wide variation of the duty cycle, PWM control presents a low efficiency also. So to avoid the drawback of the PFM and to avoid the limitation of the PWM, PSM strategy is presented as one of the efficient methods. With the PSM strategy, we can improve the control performances, and we can avoid the frequency saturation. We can avoid the wide variation of the duty cycle by varying the phase shift angle. And this is very important to improve the efficiency at the saturation zone. And also the PSM or the phase shift modulation can be applied for the whole operating zone of the DC-DC converter.
Okay, thank you.
You are welcome. Other questions maybe?
Yes, hello, Mr. Attar. This is MD Abid Hassan. Basically, I have a questions.
Yeah.
In your research, the one of the most key topics I saw it's optimizations techniques.
Yeah.
So can you please explain me in very short about what is your goal for the optimizations in terms of converter?
So the aim of the optimization effect, because you have here the structure of the Llc converter. You have the resonant circuit. So here you have the structure of the Llc converter. You have here the resonant circuit, which composed from the capacitor in series with an inductor and a parallel inductor. Okay. With the optimization algorithm, we need to minimize the values of the Llc parameters. This means the inductor and the capacitor. We need to minimize these values, but at the same time, we need to guarantee the DC bus voltage control, because in fact you can minimize. You can, for example, put the minimum values of the inductor and the capacitor to obtain the minimum cost of the converter. Automatically, the minimum cost of the EV charger. You can put the minimum values, but you cannot guarantee with a classical optimization problem. We cannot guarantee the control performances. So the new challenge in our case, in our optimization strategy, is to minimize the cost. This means to obtain the optimum LLC parameters values, which give us a good control performances in the same time, and also in the two operating modes, in G2v and V2X modes. So the aim of the optimization is not only to minimize the cost, but also to guarantee the control stability.
Okay. Okay, thank you so much.
By including the control equations in the optimization function.
Okay. Thank you so much.
Yes, you are welcome.
Yes, by doing so you know a bit, Hassan, you know
Yes,
that when you reduce the capper, you reduce the weight.
Okay.
You reduce the cost.
So there is another
This is the main objective, but at the same time, as said by Houssein, you have to control your converter at all operating points.
Okay.
Not only on some operating points. So for example, if you have the load which is increasing, you ask for more load electricity. So in this case,
the question here is then the
cannot be stable, cannot be regulated.
So the question is like this optimization technique is dynamic. It's not static.
Yeah.
So if I want to ask something very specific, like which optimization technique are you using right now for such case to find the optimal value of inductor and capacitors in terms of different scenarios, maybe loads and different torques and other stuff?
It's simple method. Yeah, Hussein can say some words about this.
Yeah, in fact, this by definition of the decision variables, in fact, of the optimization, any optimization problem, you need firstly to define the decision variable. Here in our case, decision variable consists of the LLC parameters and the switching frequencies in the two modes.
Hussein, the question of Hassan is very precise. He told you which kind of optimization method that you have used. The method that Hussein used, it's simplest method.
It is
of minimizing linear criteria. You know, it's not. It's linear. It's not linear, non-linear criteria, as you can see here.
So in fact,
only on the error between the actual value and the reference value, depending on different scenarios. And I understand the question of Hassan, because Hassan use more sophisticated and more maybe precise optimization method in order to get the optimal values.
Okay, so
for example, he can use
so gradient descent algorithm.
Yeah.
And there is another
artificial based algorithm.
Particle filters.
Very good.
Yeah.
Okay.
These are the questions like this.
In this case, you need many operating points. You know, and I don't know, in this case, you don't have a lot of operating points to say.
Yeah, exactly. Yeah. In our case, in fact, the variables are the battery voltage and the power, and we don't have for sure we don't have a lot of operating points, because for this reason we just use the fmin_con function of MATLAB, which give us directly a solution of this optimization problem.
But you can have it. You can have I don't know 1,000
for sure
data from batteries from loads. You can have this
exactly. It depends on the step. The step
exactly. And in this case, the method that are used by Hassan could be very interesting, but it will give you precise values.
Very good. Yeah, exactly. Yeah.
Of course, maybe in future, if we have opportunities, we can discuss more in details about this.
For sure. For sure, maybe.
Okay. Thank you so much. Thank you.
You are welcome. You are welcome. I don't know if maybe other questions.
Yeah, if there is no more questions, so we can stop here. If there is no questions, no more questions. Okay. So I propose to you to stop here.